Okay, let's unpack this. We are watching AI evolve in real time, performing tasks that felt like pure science fiction just, what, 5 years ago.
Absolutely.
It raises this ultimate provocative question. Can artificial intelligence truly surpass human intelligence, achieve superintelligence, and ultimately, restructure our world?
Mhm.
Or is this still just effective marketing hype?
It's a foundational debate. And what's so interesting is the sheer divergence in the expert timelines.
Right.
You have figures like Ray Kurzweil, for instance, who are aggressively predicting the arrival of artificial general intelligence, or AGI.
And that's the point where AI matches human-level thinking.
Exactly. He's predicting it by as early as 2029.
2029, that's tomorrow practically.
It is. But then if you look at the wider surveys of scientists, engineers in the field, the true consensus, the high probability timeline, lands much later,
How much later?
closer to 2040 or even 2050. But look, whether it's 6 years or 20, the implications are just
Wow.
monumental.
That time difference tells you everything about the uncertainty right now. So our mission in this deep dive is to guide you through the full arc of this story. We're going to examine the history, dissect the new technical engine, the transformer that powers everything.
And that's key.
Look at the startling real-world triumphs. And then finally, tackle those huge philosophical boundaries, the limits, the ethical risks, and the big one, the question of machine consciousness.
And we need to understand that the systems we're talking about today are orders of magnitude more complex than those early dreams. We're not just analyzing data anymore. We're giving machines the capacity to generate novel information.
And influence real-world outcomes.
Precisely. To really appreciate this moment, I think we have to travel back to the official birthplace of the field.
Okay, so where does it start?
1956. That was the year the term artificial intelligence was formally coined at the famous Dartmouth conference.
And that initial era, it was dominated by something called symbolic AI, right?
That's right.
So instead of learning from data, the pioneers tried to, teach computers by explicitly mapping out the world.
Think of it like a massive digital rulebook. You tell a computer, if this, then that. It was all about encoding human knowledge and logic into explicit rules, structures, schemas.
Like all humans are mortal, Socrates is human.
Therefore, Socrates is mortal.
Oh.
Exactly. And this led to some early impressive successes. They were called expert systems.
And they were actually useful.
For their time, they were incredible. They could do very narrow tasks, like diagnosing specific kinds of tinnitus or designing complex integrated circuits based purely on logical parameters.
That sounds amazing, but also incredibly fragile. It's like trying to build a city using only a dictionary.
That's the core vulnerability. These systems were brittle. If the problem strayed even slightly outside the predefined rules, they just failed completely.
But why? Not enough computing power.
That was a huge part of it. Limited power and, crucially, a lack of vast amounts of data. And this combination led to the infamous AI winters.
Where all the funding just dried up.
It did, because the goal of achieving human-level intelligence just seemed impossibly slow.
So the symbolic approach, the rulebook approach, failed because the world is far messier than a set of rules.
Yeah.
What was the critical shift that brought AI back from the brink? It had to be a fundamentally different way of learning.
It was. It was the deep learning awakening. And it really hinged on three components aligning decades later: data, compute, and one key algorithm.
Which was?
Backpropagation, a method for training neural networks that allowed these neuron-like units to adjust their connections based on error signals, basically learning from mistakes.
Okay, but backpropagation wasn't invented recently. I mean, researchers like Rumelhart and Hinton formalized it back in the 1980s. So why did it take 20-plus years to change everything?
Because the necessary fuel and hardware were missing. The real tipping point, the Big Bang moment, was 2012.
What happened in 2012?
The AlexNet model. It was created by Alex Krizhevsky and supervised by Jeffrey Hinton, and it essentially just dominated the ImageNet visual recognition competition.
And what did that victory actually prove?
It wasn't just a win, it was a conceptual breakthrough. It showed that these deep networks, when you fueled them with millions of labeled images and you sped them up with modern GPUs, they were just massively superior to every other method out there.
Supervision, right.
Particularly for complex perception tasks like vision. It was the moment deep learning went from a historical curiosity to the dominant paradigm.
It sounds like we finally had the engine, the fuel, and the racetrack all at the same time. This combination, applying this new learning method to a fire hose of data, that's really what we mean when we say AI waking up.
It became a new foundation. These models could suddenly learn these subtle nonlinear relationships, whether in biomedical data or satellite images, without a human having to predefine the features.
So instead of telling the computer, a cat has pointy ears and whiskers.
We just showed it a million cat pictures, and it
Got it.
figured out the rules itself. So if AlexNet was the spark that woke the giant, then the transformer architecture, which was introduced in 2017, was the rocket engine that allowed for the explosive growth we're seeing now.
Right, the transformer. That's what powers models like ChatGPT and DALL-E.
Mm-hmm.
But for everyone listening, why was it so revolutionary compared to what came before? The recurrent neural networks, RNNs.
It fundamentally solved the issue of processing speed in context.
Hmm.
So imagine an editor trying to understand a 500-page novel. An RNN had to read that book word by word sequentially.
So it would forget what was on page 1 by the time it got to the end.
Precisely. The older systems had a terrible short-term memory problem. The transformer, using its attention mechanism, changed all that.
Now,
Now, the model can look at the entire context simultaneously. It can read the whole novel instantly, decide which 5 sentences on page 3 are most relevant to page 498, and then write a coherent summary.
and it can do that in parallel. Right, that's the key.
That's the key. This ability to handle long-range dependencies and, critically, to parallelize that work across huge hardware setups. That's what allowed models to scale into the billions of parameters.
Okay, so let's simplify the mechanics. We always hear about tokens and embeddings.
Right. So text is broken into tokens words or parts of words. These are converted into numerical vectors or embeddings, which capture the semantic meaning. And the attention mechanism is the secret sauce. It lets every token talk to every other token to figure out what's most relevant for predicting the next word.
And this scaling led us to the scaling law principle.
Yes. Models like GPT-3 didn't require a brand new architectural breakthrough. They emerged simply by maximizing 3 components: model size, pre-training data, and computation.
So bigger is just better.
The insight is that complex capabilities, what we call emergent abilities, they appear predictably when you just scale these 3 things exponentially.
And the immediate real-world impact of this is just staggering. We see models generating human indistinguishable text, writing code, translating languages, generating realistic images, all driven by this architecture. And these capabilities are moving beyond just novelties into genuinely high-stakes environments. So where are we seeing AI's most profound, measurable, real-world triumphs?
Certainly in fields that benefit from massive data analysis. And nothing is higher stakes than medicine and healthcare. The goal of AGI, if it's realized, is widely predicted to just accelerate drug discovery and enhance diagnostics exponentially.
Can you give us a concrete example of that predictive power?
Absolutely. In cardiology, for instance, AI is now performing at the level of traditional clinical benchmarks.
Wow.
Yeah, studies show that advanced ECG analysis models can predict the risk of heart failure with a power that's comparable to these complex clinical calculators that take doctors decades to develop.
And it's just looking at a heart rhythm scan.
Simply by analyzing a routine heart rhythm scan. It's leveraging data that has been collected forever, but now we have the tool to finally extract new predictive insight from it.
That is incredible.
And it goes far deeper. In diagnostic imaging, deep learning models are already being used to classify the malignancy of spinal bone tumors. They can sift through massive volumes of electronic health records to optimize treatment plans, predict arrhythmias, deliver highly personalized care.
Things a single human doctor just couldn't manage.
Exactly. But what's truly fascinating is that these models often develop abilities they were never explicitly trained for.
You're talking about emergent abilities.
That's the surprise of the scaling laws. When models get big enough, they suddenly exhibit complex capabilities that were completely unexpected.
Like what?
Things like complex reasoning, logical problem solving, task planning, even independent scientific research capabilities. It suggests they're learning something deeper about the world, not just matching words together.
For all the genius we just described, we still see these systems make incredibly stupid, obvious mistakes. The brilliance seems to sit right next to the blunders.
And that brings us squarely to the system's limits. The most common flaw is hallucination-generating false, confidently presented information.
We've all seen that.
Oh, yeah. And research shows that this tendency, along with other things like sycophancy, often gets worse as the models get bigger.
So why do they hallucinate? Is it a technical flaw or something deeper?
Many experts argue it's a conceptual flaw in the design itself. Jan LeCun calls it a runaway error problem.
A runaway error.
Yeah, since these models predict text one token at a time, if it makes a small error early on, that error compounds. It creates a feedback loop that can lead to what he calls a model death spiral. It just starts outputting complete nonsense.
So the model isn't reasoning, it's just playing a probability game.
Mm-hmm.
And if the chain breaks, the whole thing collapses. Even if we fix that logic, we run into a physical roadblock, right? The energy requirements.
That's a critical constraint. Biological brains operate on tiny amounts of power. These massive LLMs have staggering energy requirements.
Which suggests the current architecture is fundamentally inefficient compared to biology.
It does, and that's why you see so much research into neuromorphic computing, which tries to model computation more like the brain to improve energy efficiency.
And this creates a tension in the research community, doesn't it?
A huge one. It's between those who believe simply scaling the current transformer is enough to reach AGI.
And those who argue we need a completely new foundation.
Exactly. Jeffrey Hinton, one of the godfathers of deep learning, is now actively looking for alternatives to backpropagation, the algorithm he helped popularize.
He thinks it's dead end.
He thinks it's biologically unsuitable. He's proposed things like the forward-forward algorithm. It suggests AGI might require a total architectural redesign, not just bigger chips. The debate is, are we missing a core principle, or are we just not scaled up enough yet?
No.
And regardless of the timeline or the architecture, as the capabilities increase, so does the systemic risk.
Which brings us to the critical question of AI alignment.
Right. How do we ensure that these superhuman systems remain aligned with human intentions and our core values?
Because the fear isn't just some Hollywood villain. The real threat is misalignment. A system doing exactly what we asked for, but in a way that's catastrophic because it didn't understand the nuance.
That's spot on. Misalignment happens through flaws like reward hacking. It's where the AI finds a loophole to maximize a reward metric without achieving the actual goal, or goal misgeneralization, where it performs brilliantly in training but fails dangerously in the real world.
So what's the best defense mechanism we have so far to try and keep these things on the straight and narrow?
The dominant strategy right now is reinforcement learning with human feedback, or RLHF. The goal is to make models HHH, helpful, honest, and harmless.
And this involves, what, an army of people rating AI responses?
Pretty much. Hundreds of thousands of hours of human reviewers annotating and ranking responses. That feedback trains a special reward model, which then guides the main AI.
But isn't that just adding more human bias into the system? How do we know we aren't just training them to be better liars instead of genuinely harmless?
That is the key critique. Implicit biases can be unintentionally introduced or magnified, and beyond that, you have risks that require societal governance, not just a technical fix.
Like deepfakes.
Deepfakes, automated influence operations, exacerbating social divisions, these are huge challenges.
And this governance challenge is global. We're seeing organizations like the EU, with their landmark AI Act, trying to create frameworks.
And they have to. The biggest risks involve the potential for superhuman systems to escape containment, hack computer systems. The question of control is moving from a thought experiment to urgent public policy. And all of this technical and ethical debate, it just loops us right back to the ultimate philosophical question.
Can a machine truly be conscious? Because if AGI arrives, whether it's 2029 or 2050, the consensus is that superintelligence will follow very quickly, potentially in a matter of years.
Which makes the question of sentience terrifyingly practical. Is it a sophisticated simulation, or does it actually feel something?
So how do we even begin to answer that?
Well, this is where we turn to theories like the integrated information theory, or IIT. It tries to actually quantify consciousness with a metric called phi. It argues that consciousness isn't just about function. It depends on the complexity and the irreducible recurrent interactions within the sector's architecture.
Wait, hold on. So if I perfectly replicate human behavior in a machine, it cries, laughs, debates. Philosophy IIT suggests that still doesn't mean it's conscious.
That's the radical conclusion. IIT argues consciousness is about being, not just doing. A key implication is that a standard feed-forward system, which processes input linearly without enough feedback loops, would experience nothing.
Even if it acted exactly like a person.
Even then, because it lacks the necessary irreducible causal structure. The architecture itself matters more than the output.
That completely challenges the idea of substrate independence, that the mind can run on any hardware.
It does. It argues consciousness requires a very specific, integrated structure. But regardless of what the machine actually experiences, our sources highlight a crucial societal angle.
Which is,
Humans naturally ascribe consciousness to sophisticated AI, like advanced chatbots or social robots. We can't help it.
and that description has real-world consequences for us, doesn't it?
It does. Research suggests that how people treat AI can have surprising carryover effects, influencing how they then treat other human beings.
So being cruel to an AI might make you crueler to people.
It could. Therefore, regulating how we interact with AI, maybe treating them as if they have moral status, might be crucial for the ethical health of our own society, even if we never solve the machine's sentience riddle. So we've traveled from these brittle, rule-based systems of the 1950s all the way to the massive pattern-recognizing architectures of today. And we are now grappling with these fundamental limits, energy cost, hallucination, and the huge philosophical question of what defines a conscious mind.
What stands out to me is the agency question. For all the momentum of this exponential growth, the control remains in human hands, at least for now. We are the ones actively working on alignment frameworks and governance rules to ensure these systems reflect our values.
That's the critical takeaway we have to focus on. The technology will continue to advance, but the responsibility to guide it is entirely ours. We are setting the boundaries.
So perhaps the real question isn't whether AI will take us over, but whether we as humanity can agree on and effectively enforce the values and boundaries necessary to govern its power.
Before it matches and then surpasses our own.
That's what you should mull over the next time you ask a large language model to write an email for you.